All right, ladies and gentlemen, today we're going to be talking about putting all of our rules for nomenclature together, because on our quest tomorrow, it's not going to be divided up into sections. It's not going to be like, here's the section on naming binary ionic compounds, and here's the section on naming compounds that have a metal with more than one charge, and here's the section on naming naming molecular compounds. It's all together. Everything's going to be all together. And while I think you've done a really great job thus far with naming things individually, meaning I tell you the rules for how you name the molecular compounds, and you did a great job with that, it's a little bit different when I mix everything up. So today we're going to be talking about the series of questions and sort of the thought process that you have to go through when you are naming compounds and everything's all jumbled. It truly, truly is a series of questions that you have to constantly be thinking of. And on the quiz, you're not going to have a prompt that says, like, answer this question first. So the very, 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 very first thing you have to ask is your compound ionic or is it covalent? We have totally separate naming rules for compounds that have ionic bonding versus compounds that have covalent bonding. Compounds that have ionic bonding, their naming is all based on charge, because that's what ions are. They're things that have charges. So it's all writing the formulas, it's all about charges. Coming up with a name, it's all about charges. But in covalent bonding, we don't have any charges. That's kind of what covalent is. We don't have ions. We just have nonmetals that are sharing electrons. So they get a different naming system, one that doesn't involve charges. Ionic compounds, metal and a nonmetal. Covalent compounds, two nonmetals. That's the very first thing that you have to ask, because we have totally different naming rules for these two types of bonding. Next question that you have to ask yourself: if it's ionic, not so much covalent, but if it's ionic, is your compound binary or is it ternary? And we have to remember that binary doesn't mean two atoms, it means two elements. Similarly, ternary doesn't mean three atoms, it means three elements. And the reason that you're asking this question, whether or not it's binary or ternary, is because this is your table E question. Remember, if it's 3, table E, that's your ternary compound. If your compound is ternary, then there's a whole other set of things that you have to do. If it's binary, there's a different set of things that you have to do. So you have to be asking yourself, is it binary or is it ternary? You're naming a compound differently based on your answer to these questions. And the last thing that you have to ask, again, this is for ionic. A lot of these are for ionic. If your compound has a metal, does your metal have more than one oxidation number? If it does, you have to use Roman numerals. If it doesn't, you don't use Roman numerals. So these are constantly the questions that should be going through your head when you are naming compounds and they're all jumbled up together. Is your compound ionic or does it have covalent bonding? Is your compound binary or is it ternary? Does the metal have more than one oxidation number? You do different things based on the answers to these questions, and that's what we're going to go through right now, kind of summing everything up. Summing up nomenclature. If your compound is ionic and binary in terms of naming, then first thing, second thing. All ionic compounds are named very straightforwardly. It's just, what's the first thing? What's the second thing? What's the name of the first part of the formula? What's the name of the second part of the formula? But we do have to remember that element number 2, the name will end in "ide." It's not fluorine, it's fluoride. It's not oxygen, it's oxide. It's not nitrogen, it's nitride. So we take that nonmetal name and we end it in "ide." We will always, always, always put the cation first. Your positive ion will come first. That's the metal. Metals have positive charges. The anion name will come second. That's the nonmetal. Nonmetals have negative charges. So it's always going to be metal followed by nonmetal. It's never going to be the opposite way around. Then you have to ask, does your metal have multiple charges? If the metal does have multiple charges, then you have to use Roman numerals. If your metal does not have multiple charges, then you do not use Roman numerals. It's inappropriate to use Roman numerals. So this is for ionic and binary. If it's ionic, if you say figure out that your compound is ionic and you figure out that your compound is binary, then it's first thing, second thing that ends in "ide," and then think, Do I need to use Roman numerals? The way you figure out the Roman numeral that you need to use, well, that's just based on oxidation numbers. So that's based on charges. That's say, okay, well, I know that I'm going to have to use Roman numerals here, but I got to figure out what Roman numeral to use. So assign oxidation numbers. Remember that the sum of the oxidation numbers has to add to 0. So figure out, what's the oxidation number on the anion, on the nonmetal, because you'll always know that. Remember, use the first one listed in the reference table because that's the one that's based on the octet rule. And then work it out. Say, well, if the metal has to cancel the charge on the nonmetal, what does the charge on the metal have to be? But if it's not binary, if your compound is ionic and ternary, if there are 3 elements in your ionic compound, then table E. Go to table E, find half of the name. You're going to have a compound, it's going to have 3 elements in it. If it's ternary, then you will see that a combo of like half of it in table E, and just name it that. Remember, like NO3 with a charge of -1 is not nitrogen trioxide. That's not what it is. NO3 with a charge of -1 has a special name. It's called nitrate. That's what table E tells you. So if it's ionic and ternary, go to table E and find half the name. Now the compound is still named the same way in terms of it's still what's the name of the first thing, what's the name of the second thing, and then you're done. So you don't need to get super complicated in terms of that naming. It's first thing, second thing, but you might have to find half of the name in table E. You have to still ask the question about whether or not your metal has multiple charges. If your metal does have multiple charges, then you have to use Roman numerals. The way it works now is that you're using the charge on the polyatomic ion that's in table E to figure out the charge on the metal. You're using table E again. So basically, if it's ternary, it's all about table E. You absolutely 100% have to use table E to determine the charge on the metal. Remember to treat the polyatomic ion like one unit. Look at the parentheses. If the polyatomic is on the inside of the parentheses and there's a number on the outside, that number on the outside tells you how many of the polyatomic ions there are. And then treat that polyatomic ion like one thing. Each of those things has that certain charge, and then assign oxidation numbers the same way that we did before. The exact same way. Going back to the 3 questions that we ask, that first question that we ask is it ionic or covalent bonding? If the answer is that your compound has covalent bonding, if it's 2 nonmetals, then naming the compound, all you do, quite literally, all you do is use prefixes to say how many of each element there are. Remember that covalent bonding is not based on ions. It's not based on charge cancellation. Because of that, you have to use prefixes to indicate how many you have. Otherwise, there's no way of knowing. They're not combining in a certain ratio based on charge cancellation because there are no charges. It's covalent bonding. No charges with covalent bonding. So we have to have the prefixes to say how many of each we have. So we use prefixes to say how many of each element we have. The second name ends in "ide." You do not reduce. If it says that you've got 2 of one thing and 4 of the other, do not reduce it down. It's 2 of one thing and 4 of the other. This is not ionic bonding. It's not based on charge cancellation. Use prefixes, say how many of each one there are, and the second name, end the name of the second element in "ide," and then you're done. The only time that you do not use prefixes, remember the exception. Remember, carbon dioxide tells you all the rules. It says to use prefixes. It says to end the second element's name in "ide," and it also says that you don't use prefixes if the first element is only 1. We don't say monocarbon dioxide, we just say carbon dioxide. That's the one time when we don't use prefixes. We'll use prefixes for 2 through 10 for the first one, and we will use mono on that second one, like carbon monoxide. We do use the mono there. But remember, carbon dioxide kind of has all the rules. If it's covalent, all you do is use the prefixes and then you're done. So if you have 2 nonmetals, if you recognize it as having covalent bonding, it's really very straightforward. So we're going to practice. So CaI2. We're going to go through our thought process. First question, is this ionic or covalent? Well, calcium's a metal. Quite honestly, the presence of any metal in these compounds is like your major tick off that, like, oh, hi, it's ionic, because we don't have metals in covalent bonding. So we identify this as being ionic. First question, is it ionic or covalent? This is ionic. Second question, is it binary or ternary? Now, there are 3 atoms in this thing, 1 calcium and 2 iodines, but there are only 2 elements, so that makes it binary. Binary means 2 elements. So we identify this as ionic and binary. That means, in terms of naming, that we say the second thing and the first thing, and then the second thing ends in "ide." But we also have to ask, does this metal have multiple charges? So that's reference table. That's, look at your reference table, look at the periodic table, you're looking up calcium, Ca. Hopefully you see that calcium only has 1 possible charge. That means that we do not use Roman numerals in this name. It's just first thing, second thing. First thing is calcium, second thing, iodide. So the name of this compound, calcium iodide. Next one, P4O10. First question that we have to ask, is it ionic or covalent? Ionic is metal and nonmetal, covalent, 2 nonmetals. We have 2 nonmetals here. We have phosphorus and we have oxygen. This thing has covalent bonding, therefore we are going to use prefixes. So prefixes, again, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. So we have 4 phosphoruses, so we're going to use the tetra prefix. We have 10 oxygens, so we're going to use the deca prefix. Have the second element end in "ide," tetraphosphorus decoxide. Next question, TiCl3. We want to name this thing. First thing that has to go through your thought process, is it ionic or covalent? Well, we have Ti, that's a metal. Automatically, that's going to make this thing have ionic bonding. Second question, is it binary or is it ternary? Well, there are only 2 elements, so it's binary. That means that we're not using table E. That means that it's just, what's the name of the first thing, what's the name of the second thing? Third question, does our metal have more than 1 charge? So we look up the Ti, find Ti on your reference table, and hopefully you see that, oh, it does have multiple charges. In fact, it's got a couple, so we have to figure out which one it is here. So Ti is not tin. Tin is Sn. Ti is titanium. You have to know the names. Name it wrong, and it's wrong. Use table S. So in order to figure out the charge on the titanium, you have to look at the charge on the chlorine. Chlorine's a halogen. We know oxidation numbers for halogens. We know the rule is that they're -1 when they're in a binary compound, which is exactly what we have here. So the chlorine is -1, and there are 3 of them. 3 times -1 is -3. The titanium, the 1 titanium has to cancel out the -3 charge that we get from the 3 chlorines. So the titanium has to be a +3. So we put this all together in the name. First thing, titanium-3. Second thing, that ide ending, chloride. So the name of this compound is titanium-3 chloride. Next up, Ca3PO42. Same set of questions every single time. First question, is this ionic or covalent? The presence of the metal, calcium, Ca, that's a metal, means that we have ionic bonding and we're going to follow ionic nomenclature rules. If you've got ionic bonding, we follow ionic nomenclature rules. Second question, is it binary or ternary? Well, count them up. CaPO. There are 3 elements that are in this compound. If it's 3, table E. If it's 3, you have to go to table E to find half of the name. This is not calcium phosphorus tetroxide. That is not the name of this little beastie. You have to go to table E to find half the name. And you will be finding, very typically, not always, but very typically you'll be finding the second half of the name. Ca, that's calcium. We know that name. So you're looking for PO4. You're looking for what is the name of PO4 on table E. Hopefully you found it. PO4, that's called phosphate. It's not called phosphorus tetroxide. No, it isn't. It's called phosphate. So We have Ca, that's calcium, and PO4, that's phosphate. One last question though, because we're not done. Does the metal have multiple charges? You have to ask yourself that. You have to think about that, because if the metal does have multiple charges, we have to use Roman numerals. So you go back to your periodic table, look up calcium, realize that, oh, calcium only has one possible charge. It's only ever +2. That means that the name of this thing is calcium phosphate. No Roman numerals, just first thing, second thing. First thing is Ca, second thing is PO4. The 3 and the 2, the Ca3 and then PO4 parentheses 2, those don't come into the name for ionic compounds, because those subscripts are telling us the ratio that the calcium and the phosphate have to be in so that their charges cancel one another out. It's understood in terms of chemistry that we know that calcium is +2 and we know that phosphate is -3. So we know when we say calcium phosphate that they're going to have to combine so that their charges cancel out. We don't indicate that with the name. And the last one, N2O. First question, ionic or covalent? Ionic, metal, nonmetal, covalent, 2 nonmetals. This thing has got 2 nonmetals, nitrogen and oxygen. That means that it's covalent. That means that we use the covalent nomenclature rules. Covalent nomenclature rules are not based on charge, they're based on number. They're based on prefixes. So we just use prefixes to say how many of each one we have. We have 2 nitrogens and we have 1 oxygen. The prefix for 2 is di, the prefix for 1 is mono. We do have to use the mono prefix on the second element in the name. We don't use it on the first one in the name, carbon dioxide. We don't say monocarbon dioxide, but we do use it on the second element in the name. We do say carbon monoxide. We don't just say carbon oxide. So in the case of N2O, the name of this, dinitrogen monoxide. 2 nitrogens, 1 oxygen. Now all this stuff is for naming a compound from its formula. Going the other direction. Now we're talking about writing a formula from the name. You have to ask yourself the same set of questions. Very, very, very similar questions. You have to start by asking, is it ionic or covalent? Because you do different things for writing the formula based on your answer to this. Then, strongly recommend, is some part of this name in Table E. A lot of ates and ites, that ATE, ITE ending, are in Table E, but not all the polyatomics listed in Table E end in ate or ite. So I strongly recommend that you scan Table E, try to find half the name in Table E. If it is in Table E, then use the formula that's in Table E. If it's not, then it means that it's just an element on its own, and you don't need Table E. You're just writing the symbol for the element on its own and going from there. So if your compound is ionic, if you've established from the name that yes, we in fact have a metal and a nonmetal, and I can tell that from the name because I've got like the name of a metal and the name of a nonmetal. If you figure out from the name that your compound is ionic, then check Table E. See if you can find half of the name in Table E. Table E is your new best friend in the entire world. Once you've done that, once you've looked in Table E, if you have found half the name in Table E, write the formula. If not, if you haven't found half the name, then it's just a monatomic ion, meaning it's just the element on its own with the charge listed, first charge listed on the periodic table for the nonmetals, right? Nonmetals, we just use the first charge listed. What you have to do when you're writing out the formula for an ionic compound is write out the charge for each ion. Do not go straight from the name to the formula. You cannot do that because the name, there's nothing in the name of an ionic compound that indicates the ratio that the ions are in. You figure out the ratio between the ions by thinking about their charges. So you need to start, if you're writing out the formula from the name, by writing out the charges for each ion, and then crisscross and reduce the charges, right? Crisscross and reduce, because if you do that, you get the correct formula for your compound. If, however, it's covalent, if you determine from the name that you have covalent bonding, then writing the formula is honestly ridiculously, stupidly easy. figure out what subscript the prefix is talking about and write it down. And you're done. That's it. There's no reducing. There's no balancing charges because there are no charges. This is covalent bonding. No charges. Just turn the prefix into subscripts. Write out the symbol for each element that's in the name. Keep it in the order that it's in. Don't go trying to mess around with the order. And then turn the prefix into subscripts, and then you're done. So, some practice. Writing formulas for these compounds. First up, phosphorus trichloride. First question, is it ionic or covalent? Ionic is metal and nonmetal, covalent is two nonmetals. From a name like phosphorus trichloride, we know we are dealing with phosphorus and we know we are dealing with chlorine. Those are two nonmetals. Additionally, in the name, the prefix, the prefix on that second element, right in second half of the name, is a major tip-off that we've got covalent bonding. So, covalent bonding. What do? Just turn the prefixes into subscripts, and that's it. Phosphorus, that symbol is P. There is no prefix for the phosphorus. It's the first element, which means that if there's no prefix, there's only one of them. There's that whole, we don't use mono on that first one, so there's only one phosphorus. Next element, chlorine. The prefix is tri. Tri means three. So we have one phosphorus and three chlorines, so PCl3. Second one, silver nitrate. First question, is this ionic or covalent? Ionic is metal and nonmetal, covalent is two nonmetals. Well, hopefully we know that silver is most definitely a metal. So we don't even need to worry too much about the nitrate part of it if we can identify that the silver is in fact a metal. So this thing is definitely ionic. We have a metal that's right there, which means that we have to think about charge. We have to think about charge. The second thing that we need to do is see if we can find half the name in table E. Now, it's not going to be the silver, it's not going to be the metal, it's going to be the second half. So we want to be scanning table E for nitrate. We want to look for that word nitrate. If it's in table E, then we're just going to use that formula that table E gives us. If it's not in table E, then that means that nitrate is just an element on its own, and we can write the symbol and then go use the charge. But hopefully, if you're looking in table E, you've figured out that nitrate is in fact in table E, and it is something there. So we want to start by writing the formulas with the charges. So silver. Use table S. Silver is not Si. Silver is not S. Silver is Ag. And if you look on your reference table, you look up Ag, you see that Ag actually only has one possible charge. It's always +1. Nitrate. We need to write the formula. We need to write the charge. Nitrate, table E tells you, is -3. Is NO3. Table E also tells you that the charge on nitrate is -1. You need that information because in order to write the formula for silver nitrate, you need to know the ratio that the silver and nitrate combine in so that their charges cancel. Well, if silver is +1 and NO3 is -1, then in order to have charges equaling 0, we only need one of each. They're in a 1-to-1 ratio, so the formula is just AgNO3. Next up, nitrogen dioxide. First question, ionic or covalent? Metal and nonmetal or two nonmetals? It has a prefix. Anything with a prefix we know is got to be covalent because that's when we use our prefixes for covalent bonding. So nitrogen dioxide, all we have to do is turn the prefixes into subscripts, and then that's it. We are done. We are finished. We don't need to reduce. We don't need to think about charges. Nitrogen, symbol for nitrogen is N. There is no prefix on the nitrogen, which means that there is only one of those things. Dioxide, well, oxide, that's oxygen. Symbol for oxygen is O. Di, as the prefix means two, so the formula is NO2. Next up, vanadium 4 sulfide. First question, ionic or covalent, metal and nonmetal or two nonmetals? Well, even if you didn't know that vanadium is a metal, The Roman numeral should be a major tip-off because we only use Roman numerals for metals that have more than one charge. We do not use Roman numerals for nonmetals. Roman numerals we use for metals with multiple charges. If there is a Roman numeral in the name, you know you are dealing with an ionic compound. And so, if we are dealing with an ionic compound, this is based on charge cancellation. You have to write the symbol for each of these things. So, vanadium. Unsure what the symbol is? Table S. Table S. You're looking for vanadium? Aren't that many things with V on the periodic table? That is definitely going to be, that is just our symbol V. Vanadium. Now the charge on this vanadium, +4. How do I know it? It says it right in the name. Vanadium +4. Next up, sulfide. The key to nomenclature, use table E. Use table E. What you're looking for is to see if sulfide is listed in table E. If it is, then you just write down the formula that table E tells you. If it's not, then you know that it's just the element on its own, and you just kind of go from there. So we're scanning table E, we're looking through table E, we're looking to see if sulfide is in table E. And hopefully we're realizing that no, it isn't. It's not in table E. If it's not in table E, then it means that it's not polyatomic. It means that it's monatomic. So sulfide, what is that? That's sulfur. That's S. So we have to think about the charge on S. For nonmetals and nonmetals only, not the metals, just for the nonmetals, we use the very first charge that's listed on the periodic table because that charge is based on the octet rule being fulfilled. So the first charge listed for sulfide is for sulfur is -2. -2 because it's got the 6 valence electrons, gains 2 electrons, -2 charge. We're going to do the crisscross and reduce method. So we get V2S4, right, when we crisscross the charges. But if you leave it as V2S4, I'm sorry, but you just got that question wrong because you want to reduce it down to the lowest possible ratio. V2S4, the 2 and the 4, they have a common factor. You can divide each of those things by 2. So when you do that, you get VS2, and that's the correct formula for vanadium 4 sulfide. Basically, it's saying that you need 1 vanadium and 2 sulfurs to combine so that their charges cancel one another out, right? The +4 on the V, the -2 on the S. We need 2 of the S's, so VS2, not V2S4, crisscross and reduce. That reduce part is critical. And the last one, cobalt-2 hydroxide. First question, ionic or covalent? Well, you have a Roman numeral. You have cobalt. Cobalt is a metal. This is definitely an ionic compound. So think about symbols, think about charges. The symbol for cobalt is CO. The charge on this cobalt is +2. How do I know it? It tells me. It tells me right in the name that this is cobalt with a charge of +2. Next thing that you want to do is focus on the second half of the name, the hydroxide. And you want to figure out, is that in table E? If it is in table E in the case of the silver nitrate, then we just use the formula that's listed. If it's not in table E, as in the case of the vanadium 4 sulfide, then we know that it's monatomic and it's just a single element on its own. So we really, really, really always want to be checking table E to see if half of the name is there somewhere, somehow. So hydroxide, we're scanning, we're looking at table E, we are looking for hydroxide, and hopefully we figure out that hydroxide is indeed a polyatomic ion. The temptation with hydroxide is that, oh, it ends in I, this must be hydrogen. No, that would be hydride. This must be oxygen. No, that's just oxide. Hydroxide is a polyatomic ion. And you see it's actually both of those elements together. It's oxygen and it's hydrogen. The charge, also coming from table E, is -1. So we have to combine these things so that overall charge is 0. The cobalt is +2, the oxide is -1. So we are going to do the crisscross and reduce. Notice we don't actually use the positive or negative, we just use the number. Now, here's the case where we have a 2 for the hydroxide. Remember, we need to use parentheses and put that 2 on the outside of the parentheses. Because that's how we indicate that we've got 2 of those OHs. If we didn't use parentheses, then the 2 would only apply to the hydrogen and not the oxygen. It needs to apply to both. It needs to saying that we need 2 of these entire big units. So the formula, CO parentheses OH unparentheses 2, cobalt-2 hydroxide. What I'd like you to do now is the sheet that says naming chemical compounds, because it is everything all together. It's nomenclature, but it's got everything mixed up. Your quest tomorrow is going to look like this, just without the questions. Basically, all it is just a listing of compounds on the front. It says name them. There are no prompt questions at all, so you have to know what questions you're asking. And then on the back, it's just a list of names and says write the formulas. Again, no prompt questions. Everything is all mixed together. So this sheet is really getting you ready for that, because you have to constantly be asking these questions. Is it ionic or covalent? Is it binary or ternary? Are we using table E? Are we using Roman numerals? Be thinking about that. Answer the questions, figure out the name, figure out the formula. Please work on this for the rest of the period.